Good morning, everybody. Boy, it sounds like you might be mildly awake. Just mildly. You're at least talking to each other, right? We haven't gotten to that point in the semester where you come in like defeated, destroyed, broken. All of those things. All right, here is the roll sheet. I did do it last week. Good for me. Keep filling it out. I think we're okay. I think everybody that was in lab is on the roll sheet, and that's a good thing because I think that this Friday is census date or something like that, where you officially certify that you're here, and then after that I stop taking them. It's college. All right. Let's see. Did that? This week's lab. So lab number 4 on Thursday. You have to bring eye protection of some kind. So it needs to be certified. It needs to have the stamps on it that says it's certified for impact resistance. If you're not sure what that means, then just about any $2 pair of Home Depot safety glasses, your chemistry goggles are impact certified. If you work in an auto shop, metal shop, wood shop, then the safety glasses they have there are also certified. It just can't be your regular eyeglasses or your sunglasses, unless they're stamped with the certification. Right? So, and we have a box of goggles. If you don't want to, forget yours, or you don't want to buy your own, then we will make you wear some sort of eye protection, or we'll kick you out. But we'll give you some soap and water to clean those off too. Right? But that's happening this Thursday. A week from this Thursday is your first exam. Chapters 1 through 4. Right? So, and how are things going so far? How are chapters 1 and 2?
Not bad.
Chapter 1 was like, I can do this, and chapter 2 was like, the cop car problem, right? The motorcycle was and then chapter 3, I looked at the scores. You're still doing it. That one's neither here nor there. Chapter 4 ties together kind of everything we've done so far. So chapter 4 is going to feel familiar because it's things we've done. We're using the same toolbox, all those different kinds of things. It's just we got to do it in 2 dimensions. And we're going to get vectors inside of it. And so everything kind of comes together. So if you're in a panic over, oh my gosh, chapter 2 is so hard, I can't, right? Give chapter 4 a chance. Because it starts to help you make sense of chapter 2, and it kind of brings everything. If you're on chapter 4 and you're still like, then we got a problem, right? And you should be grasping, getting help, and reaching out, right? Admitting that you need help, all that sort of stuff. So what's the big deal in chapter 4? Well, all that vector stuff that we talked about last Wednesday, we got to throw into our toolbox. And as bad as that sounds, like, oh my gosh, that could be horrific, it actually isn't that bad. So what I want to do is I want to show you a notation first, and then explain how we're not going to use that notation ever. This might seem kind of weird, but one of the things that we're trying to do in these classes, because believe it or not, this is an introductory physics class. You know you're in trouble in your senior year of college when you go take quantum mechanics and the book says Introduction to Quantum Mechanics, like mine did. I say, what? We're introducing you to scientific expression, and one of the, we do a lot of mathematical expression here. And so what I'm about to teach you is going to carry through for your entire 4 ABC career, right? But very soon here in about 10 minutes, we're going to dispense with that notation and kind of simplify and do very specific chapter 4 things. We had this set of equations, right, where we had relationships between speeds and accelerations and time. We came up with this whole toolbox, right, that had it. I just sort of gave it to you. I never showed you where they came from. How many different directions can a final velocity point?
2. Any.
Yeah, it answers all of them, right, okay? In other words, the v in that expression right there isn't a number. It's a number with direction, right? It's a vector. Same thing for the initial velocity. The same thing for the acceleration. Time in physics we don't treat as a vector. We treat it just as a scalar. It has really only one direction, which is forward. But this is a vector equation, right? And I made it a vector equation by just drawing arrows at the tops of things, right? No problem. We run into other situations like the second equation. How did we write it before? Delta x. I can't write x now because I need something that is a statement of position that's generic, that isn't x, that isn't y, that isn't z, because those are very specific directions, aren't they? You have 20, what, 3 more choices from the alphabet?
Do you know?
We're going to use R. Now, S I have seen, but it's very rare to see S expressed as a vector. Usually S is a very generic distance. It doesn't have direction. So if you see S floating around, it typically isn't a vector. The vector is R. Now, here's a part of where normal usage, or shall we say mathematical usage, and physics usage come into conflict. Because as soon as I write down R, what do you think that is? It's a radius, right? And sometimes it is, but other times it isn't. In physics, R is a generic position vector. So if you know where something is in three-dimensional space, physicists will define a vector that points from the origin to the point wherever you're talking about. And we call that the position vector. It doesn't necessarily the radius of anything. It's just this generic. So generic displacement would be delta R. So I want you to start holding in your brain, right, the fact that, these symbols don't necessarily mean the same thing that I've been taught all my life, right? The symbols can actually change their meaning depending on the context that they're in. And again, if you can hold any thought of what I'm saying here for this 3 minutes, it's that one. That the symbols are negotiable, right? We're looking at context. If we've got this equation and we know we've got, velocities and accelerations and times together, then regardless of what I could put emoji on the left-hand side, right? And what would the emoji mean? Some sort of displacement, some sort of distance, right? So try not to get hung up on what the actual symbols are. I know, it's hard. I did it too as a student. If it wasn't delta x, my brain flipped out. But we have to start getting used to this idea of reading the relationships independent of what the actual written letters might be. All right, and then there's the third one. Squared. And again, we haven't taught you how to multiply vectors yet, okay? So we're not going to really worry about that. But to just show you how, and there's what I consider the complete toolbox. To show you what the power of a vector really is I didn't write down just 3 equations. I actually wrote down 9 of them. And how did I write down 9 of them?
Putting direction.
This, we'll just do the middle one here, okay? It can be written 3 different ways. It can be written as delta x equals v naught xt plus 1/2 axt squared. Can you guess the second way it can be written? V naught yt plus 1/2 ayt squared. And the third way? And it can get a lot worse because maybe we're not working in Cartesian coordinates. Maybe we're working in cylindrical coordinates or polar coordinates or spherical coordinates or inverse spherical coordinates. Yes, that's a thing. And it's just like, right? But this compact way of being able to write things as vectors becomes very standard, right? So you'll see sometimes on the internet or in other books where they'll write out the vector form, and in the very next line, all of a sudden, it's sprouted all these x's and y's or whatever, right? Okay? They've taken it from the step of being general to a very specific expression for the problem. So what we're going to do for the rest of chapter 4 is, first of all, don't do this in your notes, but we're going to ignore z. We're going to do 2 dimensions. Okay? Third dimension isn't actually that exciting yet. We're going to do 2 dimensions, and we are going to constrain our toolbox with some boundary conditions. We're going to set some limitations on the kinds of situations that we're going to be able to work with.
You said that our notation is only common within 3 dimensions, so
No, 2 dimensions as well.
but not like 4 or 5.
Yeah, oh yeah, no, it generalizes to every dimension you want.
Okay.
Currently we're at 11, I think, in M theory, so yeah, try not to worry about anything past 11 dimensions. I have trouble with 1 dimension sometimes. Like, I want to go that way. So, yeah, watch out. Okay. What we're going to do is a special case called projectile motion. So, projectile motion is something that an object does if gravity is the only force that's acting on it. So instantly, what can you tell me about all objects that are in projectile motion?
Free fall.
They are in free fall. And we've done free fall before, right? We drop stuff, okay? So how is this any different? Well, instead of just dropping things, what are we going to do now? We're going to toss them, right? Okay? It's not going to just have vertical motion. It's also going to have sideways motion. So that when I give it both vertical and sideways velocity, it describes an arc through the sky. Right? So projectile motion, again, is any motion where gravity is the only force acting on it, means gravity is the only acceleration that the object is experiencing. Is this projectile motion? Yes, it is. Okay? It happens to be one-dimensional projectile motion, but it's still projectile motion. Is it free fall? Yes. Is this projectile motion? Yes. Is this free fall? Yes. This? Yes. Yes.
He's got 2.
Are these balls, as long as they're not in my hand, undergoing projectile motion?
Yes.
Are they? Yeah, as long as they're not in my hand. Because if they're in my hands, then that's not just gravity only, right? So yes, I can lecture and juggle. Right, okay? So practice that at home before you try that in public. All right, so how are we going to deal with this? So what direction does gravity point?
Down.
Sure? Yeah, points in, actually. So, as we write out our toolbox, okay, and I should probably put the toolbox on the board. I'm going to write on the board. Okay. So, I'll draw the final toolbox right there. Let me get an intermediate toolbox going, okay? We could write these equations all down for x and y, right? So for example, and you may not want to write down what I'm about to write down on the iPad screen, okay? Because I'm going to destroy it. I'm going to go through with a flamethrower. I'm going to get rid of all of it, okay? If I write all these things down in terms of x, probably wrong because I'm going really fast, right? And then I do it again in terms of y. Okay, are you in a panic?
No.
Why not?
Ugly.
Because I'm here to hold your hand.
No.
Why? Are these all the same thing? Whoa.
No, one's and components.
Okay, there's different components, but the ideas behind them are all the same, right? The tools haven't changed. The third equation is still useful if you don't know time. The second equation, if you don't know your final velocity. All those things still carry over from chapter 2. Just we have it in 2 dimensions. What we're going to do for the case very specific of projectile motion is we are going to say, okay, the acceleration in the y direction is going to be that. Where'd that come from? Gravity, right? And the acceleration in the x direction? 0. We want gravity only. If there was another force, say air resistance, right? Then there would be some component of acceleration in the x direction. This would be speeding up or slowing down. So we're not going to do that. We're going to do the case where there's no air resistance, the objects don't have wings or lift or any other that kind of stuff. You're just going to be flung through the air. If we do that, if we stick, right, that condition in, then what happens to my first red equation up there? Right? Is that true? If there's no acceleration, is the speed that you end up with the same as the speed you start with? Yeah. Kind of the definition of acceleration, isn't it? Is that useful?
Yes. No. Not really.
No. Which tells you it's got to be math. True, but useless. So, what about the second one? And then the next term is? Why is it 0? Because we're sticking in zeros for all these terms that have accelerations in them, right? Now, is that useful?
Yes.
Yeah, distance equals velocity times time. Who knew? And then the last one, again, is a repeat of the first one. So it turns out that the X portion of this toolbox, specifically for projectile motion, collapses down to just one thing that we're kind of like, well, we knew that. Distance is velocity times time. Done. The Y toolbox doesn't change. Now, what do I mean by that? I mean it doesn't change in the sense that I am going to always write it as AY. I, Mr. Balo, will never write negative G into these equations. Your book does. Lots of physics textbooks do. Okay? But they are preparing you to fail later on. Because what's going to happen later on? It's not going to be just gravity. And why do I turn around and always smile like that when I say things like that?
Because you know how ready for the day.
I'm trying to freak you out a little bit. Right? I'm trying to reassure you, right? But it's fun. It's really fun. And we spell fun P-H-U-N in physics. And that just means it's really stinking hard. So, while the number that we eventually substitute in for this acceleration is going to be negative 9.8, assuming up is positive and down is negative, I don't want you to think, I'm going to write it on the board, please don't write it down, okay? I don't want you to think, because you'll see this, okay? As soon as I write that down, students go, oh, it's a different equation. It's not a different equation.
7 minus 7.
It's the same, it's the second one, right? Don't hard code in the minus sign or the G. What if we go to the moon? What if we want to make up be negative? We have this power. Why destroy it? Why limit ourselves? Don't do that. I'm trying to teach you a better way because I know what's coming, right? Okay? And if I can give you practice here where it's relatively safe and easy to do this kind of thing, then later on when we get there, you're going to be like, okay, this isn't quite as bad. So, got to kind of, it's dangerous, but you have to trust me a little that I know what I'm doing. Okay. One other thing about projectile motion. We have to figure out what we're going to do when we have, say, an object that's launched at an angle of 55 degrees at a speed of 13 meters per second. The equations over... my board toolbox here. Technically, I'll write down this fourth one. That really is kind of the only change to the toolbox in chapter 4. But I'm hoping you're seeing that it's the same friendly toolbox as before. We put more tools in it, kind of, right? But in the end, the only horizontal equation that's any use to us was that second one, right? Because all the other accelerations disappeared. So we need to... Can we put 13 in here for the initial speed? Why not? Because 13 is not the vertical component of the velocity. 13's off at some angle of 55, isn't it? So how are we going to find the vertical only piece of that initial velocity? Oh, chapter 3. Right? Okay. How are we going to find the x component of the initial velocity? Chapter 3. We've got to break these velocities, the initial velocities, up into their component parts, which is why we did chapter 3. Now, for those of you that are contemplating the future, could the acceleration have components? Yeah, vector. We are setting again for projectile motion. The horizontal component is going to be 0. We're going to not do anything in the horizontal for chapter 4. And the vertical we're going to set to gravity. That means that if the object strikes the ground, is that still free fall? No. Why not? Something besides gravity is happening, right? Again, the box only works if the acceleration doesn't change. The acceleration is only free fall. The acceleration isn't free fall. We'll get there. We'll get there. So, what would, for this velocity I've written down right here, and maybe more generically, an initial velocity at some initial angle, what would I write down for the x component of this initial velocity?
Cosine.
Why is it cosine? It's touching the angle. And then what would v naught y be? It would be, we'll do it in blue, v naught sine theta, right? Sticking up either right there or right there, doesn't matter. My advice to you is that if you're given a problem that says some object is launched at an angle of 15 degrees at a speed of 45 meters per second, before you even think about or read the rest of the problem, just find the components. You're going to need them, okay? Right? Just break it up into the components, get into x and y, and away you go. All right. Let's do a quiz. All right, so by way of example, okay, because we've done a lot of concept and we've kind of got our framework down, and what I want to do is just start doing it. As a matter of fact, with the exception of some circles at the very end of chapter 4, I'm done with presenting content to you in chapter 4, and away we go with applying our problem-solving method. This is what we're going to do before. Let's make up this problem together. I'm not going to give you a word problem because, quite frankly, the universe doesn't give you word problems. What it gives you is observations, right? And you look at something and you go, oh, really? That's cool. I want to understand that. And then before you know it, you've got a PhD in something you don't know about. So, one more thing to mention about this travesty. Sometimes you will see this. In fact, I think you see this in your book in chapter 4. Okay? Again, what did they do?
That's the X.
They hard-coded in the component of velocity, didn't they? And again, this is a mistake as far as future-proofing your brain. Okay? Because the y direction isn't always sine. No. Right? So, and again, this equation looks completely different from that one, doesn't it? No, it doesn't. Because when you develop a level of expertise, I'm not saying you're an expert, but an expert thinks in terms of these are the same equation. A novice, when seeing this information for the first time, compartmentalizes and says, well, this one is different from this one. And so that's why novices struggle. They have a lot of cognitive load because they're trying to understand relationships between things when they don't see relationships between things. But if you can start thinking at that more expert level, and that doesn't require really it's not about innate talent or anything. It's just being taught to see that these two equations, in fact, are saying the same exact thing. They have the same relationships between all the different players in it. So the more that I can encourage you to try to think at that higher level, the smoother your experience in this class is going to be. All right, so let's get rid of this garbage. Stick with that. Give me an object that you would like to see launched off of a cliff. A backpack?
Physics books.
Wow.
That's always, every once in a while I hear Mr. Balo, but that usually happens later in the semester. A backpack? Seems kind of boring.
I know.
In lab, we told you to chuck us off the
A what?
a mountain.
You want to see a mountain thrown off of a cliff?
A caboose.
A mouse.
Another cliff.
Another? We are getting so meta here. Can we do a bonsai mountain? I don't know. That's caboose. I like a caboose.
That's the
But I'm struggling with the mountain. Can we do a cave troll?
Can we do buffalo since they fall off mountains anyway?
All right. So we're going to launch a buffalo or a cave troll. How many of you want a cave troll? How many of you want buffalo? How many of you don't care? All right. We're going to go with buffalo. Majority spoke. So, okay. Somehow, some way, a buffalo is launched off of a cliff. We'll leave it to the reader's imagination as to how that transpired. And I'm going to give this buffalo, I could let you make up numbers, but then you'd have to do all the calculations, and we're going to go a little bit faster than that. So the buffalo launches off the edge of this cliff. Cliff is 75 meters high, okay? And it's sitting out next to the ocean, okay? So initial speed of 40 meters per second at an angle of 50 degrees. Our task is to discover everything. How far away from the cliff does the buffalo land horizontally? How long is the buffalo in the air? The maximum height that the buffalo obtains over the ocean. What kind of salad dressing the buffalo likes. I mean, the world is our oyster. We can figure all of this out. So, where do we always start?
Do we find the X and Y components? No?
We can. I did say that, right? As soon as you're given these things, you might as well just get up. So let's do that. Let's do that. But that wasn't the answer to my question. You always start where in the problem-solving process? Visualizing, making a list, categorizing your information. So we'll call this categorizing the components of the... So what will the x component of the velocity be? What do I write down? 40 cosine 50. And why is it cosine?
Because you're looking for the x component?
Yeah. Not because it's the x component, because the x component touches the angle, right? And then there's going to be a y component over, again, you can draw it either way. V naught y will be 40 sine 50 degrees. So when I did this, and check me, because I think people are already calculating them out there. Get your calculators out. Follow along. I got 25.7 and 30.6. Does anybody want to disagree? No. Okay. We'll go with it. All right. So another part of our visualization.
Question.
You have a question, Carl? Go for it.
Is that those are the knots?
Those were the initials. The initials. I'm putting them back. Don't worry. I'm just going to put them over there because I put them in my way. So those are the initial speeds as it launches off the cliff. Okay. What do we do? Visualization.
Magnitude.
What?
Don't you just add them up and square root?
Well, we could, but that just gets us back to 40 and 50 degrees,
Oh, yeah.
right? Already this is where we came from.
What am I trying to?
Will we have what we don't have? Make a list? Sure. Question?
Yeah.
Everything.
You need the time.
And I know you're sitting there going, but Mr. Vader, just tell me which one. The answer is, it's physics. We find everything.
We don't find the time right now.
We went out and we measured the mass of the universe, and then we counted the number of stars, and we found out we were off by 90%. Right? So what did the physicists do? Invented dark matter. So everything. We want everything. And what's everything? Well, it's sitting right here in front of us. What could we know and what could we not know? Just read it out. We could know or not know.
I'm so sorry.
We could know or not know the initial or the final vertical velocity. All right? Could we know or not know the initial vertical velocity? What about the acceleration in the y direction? Where am I getting these things? I'm not making them up. I'm just reading. These are the pieces, parts of my tools, aren't they? They're pieces of data that can go into this model, projectile motion, and there are possible things to know and not know. What comes next? Delta y. We already have v naught y in our list, don't we? And t. And we don't need a half. Ay, t, it's all good. Vy, v naught y, ay, delta y. What comes next? Okay, so for the chapter 4 list of things we could know and not know, I pick up a delta x and a v naught x, don't I? All right. So we go in here and we start writing down what these things are. Do we know the final y velocity? And what do we mean by final y velocity?
Right before it hits.
Is it where it hits the water?
It's like the moment right before.
Or is it the top of its flight? The answer, it depends.
What is
Are you looking for maximum height above the surface of the ocean? Then you might want to put your final point at the maximum height. If you just want to know how long the thing's in the air, then we'll put our final point where it hits the water. I'm going to come back over here and I'm going to draw, whoops, a very bad looking parabola. Okay, so there's kind of a, I don't know if it's exactly that, but it gives me, again, an idea, right? I've a picture in my mind to anchor myself to. And so if I say, okay, I'm going to make this my final position down here, right? So I'm going to do the whole enchilada. We're going to find, let's start with time. How long is the buffalo in the air? Okay? So we're going to find out how long the buffalo is in the air, and we're going to do that by initial point being at the top of the cliff and final point being down there in the ocean where the buffalo is now with the fishes. Is everybody with me? I had to go in because the problem is not a word problem, it's a natural problem, and I had to specify what I'm doing, right? I had to conceptualize of where I was and where I wanted to be and the thing I'm going to find, and change my inputs based on those definitions. This is how the universe works. All right, so with that in mind, and the fact that we're going for time, I can kind of automatically go, well, I don't know what the time is, and I'm looking for it. So I'll circle that one and get that one out of the way. Okay, back to my question. Do we know how fast the buffalo is going when it hits the water in the vertical direction? No. And those of you that wanted to say, well, it's 0, it's not 0. Why is it not 0? It will eventually be 0. But I can only do this problem as long as gravity is the only force accelerating. As soon as the buffalo hits the water, that's not gravity anymore, right? So again, the toolbox only good for constant acceleration. What will that acceleration be? We can go ahead and just drop that right in there, negative 9.8 meters per second squared. Okay, so we don't know what the final speed of the buffalo is when it strikes the water. Do we know the initial vertical speed of the buffalo when it launches?
Yes.
Yes, what is it? It's not 30.6. It's close. It's positive 30.6. And you're going, oh, yeah, I said that, Mr. Balo. Think it too. Don't forget to check the directions of things. Even if you think you know the direction of it, check it. Go ahead. Wasn't listening.
Oh, it's okay. I'll be able to voice. So I was wondering, you mentioned the acceleration is due to gravity, which is 9.8. Is it always going to be negative, or are there situations where it won't be negative?
There are situations where it won't be negative, and that starts in chapter 5.
Okay.
Yeah. So this brings up a good point, right? Don't fall into the trap of thinking that that's always negative. Little g is not negative. Okay? Little g is a number. What's the number? 9.8. The direction, we have control over. Which is, again, why I hate those equations that hard-code it in. Because we need to start practicing with that idea that we set the terms, not anything else. All right, delta y. Do we know the vertical distance that the buffalo goes through? Yes. What is it?
75.
It's not 75. It's negative 75. Why is it a negative 75? It ends up lower than where it started. It's moving down. But Mr. Balo goes up first. I know. And so does the toolbox. Because if you tell the toolbox that the delta y for the buffalo is positive 75, then what does the toolbox think is going to happen? That it launches and ends up higher than where it started. Is that what's happening?
So in another situation, if it were to be launched, but it stayed on the cliff, then that would stay positive. But because it fell off the cliff, it would be...
If it stayed on the cliff, the same elevation, the delta y would be 0. There would be no change. Yeah. Positive if it lands higher than where it started, and negative if it lands lower than where it started.
Okay.
Everybody get that? Because you'll have problems in your homework to do both. All right. Do we know how far sideways?
No.
Nope. And if I was going to draw that on this diagram, right? I draw it like that. It's the horizontal distance. I see some students sometimes wanting to draw, like kind of finish the triangle, right? Got 75, got that, right? Things don't go in straight lines off of cliffs like that, right? Okay, so you can't just draw from the starting to the ending. It's the horizontal piece, how far horizontally it moves, right? Vertically we broke out, horizontally we break out too. So we don't know what that is. Do we know how fast it's going in the x direction at the beginning?
Yes.
Positive, good job. We're starting to learn. Okay. Again, because you're newbies, I really strongly advise you that when you make a list like this, that you go back and check the directions of everything. Have I gone through, right, and listed everything I know and don't know and made sure that I've got it pointing the correct direction? Am I telling my tools the reality of the situation? All right. What do you think for strategy here? We're after time, based on what we know and what we don't know.
Well, we know how to solve for delta. Oh, no, wait, you don't have to.
Find out what it takes to get to the.
No, we can find it.
We can find the final velocity and then find the time that it takes.
We could, right? Use the third one, right?
Use the second one.
And once we know, like maybe we want to know how fast it's going when it strikes the water, right? Then once we know, we go out here and put it and find the time. That's some algebra I probably would screw up. Knowing myself, inability to write stuff properly. What's the second one got going for it? It's only one unknown in one equation, isn't it? So I don't think we've done this yet in this class. So let's not avoid it. Let's just do the second one.
So if I were to pick the third one, I have to do two different equations because I have to do the third one and then I have to plug that into the first one. So
Yeah. If you're happy with that, great, it's fine. Hint, hint, that's a way to check. All right. So my strategy, or at least the one I'm going to employ right now, is that I am going to use the second kinematic equation and solve it for t. So I copy it down. Notice I voiced my strategy. Again, I'm encouraging you to write down your strategy in case you get lost. And then I got to solve this for t, and I'm staring at it, and I'm going, okay, that means quadratic. I'm quadratic in t. I've got a t and a t squared. And so if I'm going to do a quadratic, I'm going to do a quadratic equation. I'm just going to throw the numbers in. I'm not going to bother doing this symbolically. Okay? So I'm going to throw my numbers in. Minus 75 and a positive, and I got to be careful, v naught y. I often put the x one in for some reason. T minus 4.9 t squared. And where did the negative 4.9 come from?
Divided by half.
It's 9.8 divided by 2 is 4.9. You're going to do that so much that you're going to make a mistake at some point. I make this one all the time, where little g becomes 4.9. Right. I tell you that not so that you make that mistake, but so that when you do make that mistake, you realize you are an excellent company. Right? Everybody does it. Try not to do it. Watch out for it. Okay, but yeah, it's a thing. When I was tortured in high school in my math classes, I was told that I had to move everything over to one side of the equal sign and to try and always make the thing in front of the x squared positive. I learned out later that that's not true. It doesn't matter, but, you know, teachers do bad things to their students. Minus 75 equals 0. And now I've got something that's in the form of ax squared plus bx plus c, where my a is 4.9, my b is negative 30.6, and my c is negative 75. So now that I've got it in that format, how do I solve it?
Plug it in. Just plug it in.
You like quadratic?
that. I think I can just do 4.9t squared minus 30.6t minus 75 equals 0 for t. So, check and make sure that the almighty gods of the internet interpreted my input correctly. They did, right? And then they gave me very scary things. I want approximate forms. That's much better. Right? Okay. Question?
Oh, he timed everything by -1.
I moved the negative 4.9t squared over to the left-hand side. Became positive. I moved the 30.6 over to the other side. It became negative. And the negative 75 stayed put on the left-hand side. Just say negative. I did that right?
Yeah.
Is that how you were taught to do? No, you were taught to just go to the
it's a
internet.
calculator.
Yeah, plug it in your calculator, whatever. On the test, are you allowed to use the quadratic solver in your calculator?
No.
Yeah, I don't care. Okay, just make sure that you tell me that you use the solver in your calculator, right? If I see you go from one step and then all of a sudden have answers, I'm just going to assume you cheated, right? So provide documentation for what you did, okay? Are you allowed to use Wolfram Alpha on your exam? No. Okay? Good. Now, if I had the proper setup and I had lockdown browsers that only let you go to like Wolfram Alpha, right, or something like that, I'd be more than happy to let you use the internet, right? Okay? But what I don't want you to do is sitting there Googling every single problem on the internet, right? You need to find out what you know, not how good your search skills are. All right, so what did it tell me? It told me two things, didn't it? Okay? And why did it tell me two things?
Because it's plus or minus.
Because it's quadratic. And there's got to be two answers. 1.88 and positive 8.13. Okay? And those will both be seconds. Standard units in equals standard units out. So, don't answer this out loud. Which one do you pick? Shh, shh, shh. Okay. The reason I don't want you to answer out loud is I don't want you to embarrass yourself. Okay? If you said, well, the positive one, you're wrong. Why are you wrong? You're actually right, but you're wrong.
Time doesn't have direction.
Because math can lie to you. Now, the mathematicians in the room now they want to kill me. Okay? But let me explain. Math doesn't lie. Math is pretty good. Okay? But it doesn't care how you feel or what you're looking for. It will tell you exactly the question that you asked. In this case, how long does it take for the ball to be at negative 75 from its launch point? And the math spits out, well, that happens at two places.
Right.
It's parabola, right? In fact, it told us the time for there and the time for right there. One of them is physical, one of them isn't. And you can do some hocus pocus to change the signs around. It's not that difficult to get this thing to spit out positive 1.8 and negative 8.13. So, going for the positive answer is not safe to do. Get rid of that idea in your brain. Okay? What is safe is to argue physically what must occur. Does this buffalo have a lot of the parabola or a little bit of the parabola to do?
A lot.
It's got a lot of the parabola to do. Can you see it? It's got to go up to its maximum and then come back down. That's a bigger portion, because the mathematical curve, the parabola, right? The physical portion is from the top of the cliff down, which represents the majority of the parabola. So I'm going to pick the one whose magnitude is bigger, regardless of its sign. Because what does the 1.88 represent? The shorter portion, the dashed portion of the parabola right there. Which for our problem, is that a physical thing? Is it real? No. But if the buffalo were launched at the base of the cliff, it would take 1.88 seconds to get up to 75, and then it would take another 8.13 seconds to come back down. That's what this is trying to tell us. Okay? So it's not like one of the answers is wrong, and I should just throw it out and ignore it because it's negative. I need to think about what the numbers are that these mysterious mathematical methods are giving me. Because there's real value in understanding where they come from. All right, so I'm going to go ahead and pick the 8.13 seconds and argue that that is the one that corresponds to the physical setup that I have in this problem. Not because it's positive, but because my buffalo has to do most of the parabola's path. Is everybody okay with that? Think about it. Okay. Get back to me if you're still confused. Okay, could we find delta x? How far away from the edge of the cliff the buffalo lands?
Yes.
How are we going to do that?
V naught x is c.
We've only got one, right? In the x direction. So if we wanted to find that one, we could say, well, I'm going to use the only x equation I've got. I know my v naught x, 25.7, positive. I know my time now. My time is what? 8.13. Okay. And then I would find that this is... can't read. 208.7 meters. Boxes are the accepted way in physics that we say this is our answer. All right, what else could we find out? Could we find out how fast the buffalo is going when it strikes the water? Do you think this is important information for the buffalo to know? Okay. Okay, so notice, I asked that question very casually, but it's got daggers in it. What did I ask for?
The final velocity when it hits the water.
Okay. Is the final velocity, is the symbol for the final velocity of the buffalo when it strikes the water written anywhere on the screen? Is the symbol that represents the buffalo's final velocity when it strikes the water written anywhere on the screen?
Change the variables to find it.
Final velocity in the y direction is not the final velocity of the buffalo when it strikes the water. Why?
Because we have to take it into the x component.
Because there's x components of that as well. When this buffalo hits down here, there is a Vy, but there is also a Vx.
Well, you only asked for the VY.
No, what did I ask for? I asked for the final velocity of the buffalo when it strikes the water. Not how fast is it going vertically, not how fast is it going horizontally, but how fast is it going? What do we have to find if we're going to find either the speed that it strikes the water or the velocity that it strikes the water? We have to find that. And that is a vector. And that vector consists of two parts, a horizontal part and a vertical part. So that's why I said that question had daggers in it, right? It sounds so innocent. Well, how fast is it going when it hits the water? If you solve for Vy and you plug that into Wiley Plus and it comes back with a red box, that's why. The vertical component is not the total speed that it has when it hits the water. It's only one part of the total speed. So, to find out what that V is, I have to find Vx and Vy. Well, how do I find Vx?
It equals v naught.
It is 25.7. Why is the final x speed the same as the initial x speed?
Acceleration.
No acceleration in the x direction. Okay, we got that one. How do I find Vy? Just
Plug it in.
algebra. I love Carlos. Just algebra. Let's do some physics instead. Can I use the third one?
You can use the first one.
Can I use the first one?
Yes.
Okay. Which one's better? Which one's worse?
The second one, the third one's better.
Hunter, why'd you say that?
The first
Because
one's
it has
better.
more variables.
More variables? More variables is better? I actually agree with Hunter. I think the third one's better, but not for that reason.
Because you have more knowns that you started with.
Because time is something I found. And it could be wrong still, right? Whereas this third one starts with things that I have been given, right? The delta y was given. I know this was given. I found this. But this gives me, right, a y speed. So, what I could do is use the third one since it doesn't have anything that I found. And then I could also do the first one using the time that I got and see if I get the same number. If I get the same number, what does that mean?
You're right.
My t is probably correct. And there's a check, right? So, checking your work should be a part of the process, not something that you do at the end or just wait for the green box of joy and gladness. So, what was my strategy? My strategy was use the third one. And solve it for the final y velocity. Done. In my head. And stick in some stuff. V naught y is 30.6 squared plus 2, negative 9.8, negative 75. I got 55.3, no. I got something I can't read. 49? 49? Plus or minus 49. Ooh. So what do I pick? Positive or negative?
Negative.
Why do we pick the negative 49?
It's going down.
It's going down at that point. Oh, no box, Mr. Baylor, because that's not the final answer. With that Vy now, I need more room. So what I've got now is I've got the buffalo coming down, striking the water, and at this point I have a Vy and I have a Vx. The Vy is negative 49, and my Vx was what? 25.7. 25.7. So how do I now find what this master velocity is? The combination of the x and y components?
B squared, C squared.
Pythagorean theorem. 25.7 squared plus 49 squared. I dropped the minus sign because I'm squaring it anyway. And I got 55.3 meters per second. Okay, that is a speed. It is not a velocity. What's missing?
Direction.
Direction. So if it asks for speed, then I'm done. But if it asks for velocity, I have to give it that magnitude and what else?
Negative.
Some direction. How would I find the angle I specified right there?
Anti-sine.
Arctangent of y, negative 49 over 25.7. Negative 62 degrees.
62.
So what does that mean, negative 62 degrees?
It's on the.
Below the x-axis? Okay, so I could leave it as negative 62 because all angles specified without reference mean it's measured from the positive x-axis. Your Wiley Plus and other online homework systems often insist that you answer as an angle counterclockwise from the x-axis. What do they call that? Reference angle? Something?
Reference angle.
I don't remember what it's called. Right? But what they want typically is the angle all the way around. Right? So if you were to type this into, check it, make sure and see, read the question, because it often will say, what is the angle as measured from the positive x-axis counterclockwise, right? If it says that, then you got to go all the way around instead of dropping down. So what would we have to do to find it from all the way around?
Minus from
360 minus 62 would give us that reference angle, right? Okay. So again, just watch out for your homework systems. They sometimes ask it for a funky, answer. You experienced this in chapter 3 yet, where they give you the angles east of north? What direction is north? What direction is east of north? Right? Okay? So, yeah, watch out. Because sometimes they'll ask you for what's the angle from the positive x-axis or positive y-axis, from the negative y-axis, right? They'll ask you from all over the place, and so it gets hairy after a while. What are we going to do on Wednesday?
Chapter 4.
I'm done with chapter 4.
Yeah.
No, I'm going to show you more examples. Okay? I've showed you one example today, and by the way, this is the problem we'll be doing in lab. We'll fit, not Buffalo. Not I'm really worried. Okay, we'll be launching metal balls, right? Okay, simulated Buffalo.
Keep one up.
But we're going to be doing time of flight. We're going to be doing range, okay, measurements of those. On Wednesday, my intent is to continue with chapter 4 and show you variations on a theme. In other words, there are other things that we could be looking for besides time and finals. We could be looking for initial velocities and all sorts of things. So we'll continue to play with this model over and over and over again. See you then. And where'd my roll sheet go?